Okay, we'll take off from where we left off in the last lecture. And that was where we were showing the coordinate system for space and time. In a moving frame, and that is a really moving frame that we're imagining here, can be made with zeros of the waves. And that involved half sum and a half difference of the phases of the right and left waves. And here we're just kind of faking the system that we would really be imagining, and that was either Bob is between two very rapidly moving 3C over 5 600 terahertz lasers, one directed this way and another directed this way, or he's moving, they're both sitting still, that's their frame. And the thing that we actually have pictured is the cheap experiment, and that's one that doesn't require you to pay for something that goes 3/5 the speed of light and weighs several hundreds of pounds. The tuning of a laser. Actually, this is a way to do a very delicate kind of acceleration. If I leave the frequencies alone, it's not an accelerator, it's a velocirator. And it's making something in here that has a speed that can be pretty fast. All you have to do is get double the frequency here and up to that one, and you are making a wave that would go at more than half the speed of light, 3/5 the speed of light. And we'll talk at the end of the lecture that comes next time where we talk about accelerated frames. And it's pretty easy to make that by just tuning, and very delicate sort of accelerator can be built. Now, I would like to very quickly at the beginning of this go over the geometry that goes with the algebra. We'll do them sort of both at once. The algebra that I'm thinking about is the algebra that involves these vectors. A phase vector, the so-called pitcher's mound, this one, that's made out of half the sum of the vectors that represent the ultraviolet, or more like almost X-ray, this giant vector here that has twice the frequency that we had before. Before we changed the frequencies from 600 each to 1200 and 300 respectively. The right moving vector represented here in frequency wave number space, that has a coordinate in these frequency units 1200 hertz, and then the c times the wave number, that's also in units of 300 terahertz. It's got 4 of those units, and the vector is at 45 degrees, making the what we call single coherent wave beam, and then coming from the other direction, that is this direction, this vector pointing in the direction that beam is going. This one has the inverse of the blue ship, and that makes a red ship. But we're talking about a vector here that has e to the minus rho in both positions. But in this case, this one has a minus sign because that's the actual spatial part. This is the frequency part here. So it's plus e to the minus rho, and then minus e to the minus rho there. So it might be worthwhile just jotting that down on the graph that you have first, up in the upper right-hand corner, using a purple color appropriately, I'll indicate this as a little two-dimensional vector with those values for the blue shift, e to the rho and e to the rho. For the spatial coordinate, that's this one right here, which has a value of 4 in these units, the units of 300 terahertz. And then at the other end, this vector down here is also a two-dimensional vector. I'm indicating it with a minus e to the minus rho and plus e to the minus rho. Okay, so that one is a vector that is just if you were to take the 300 terahertz units as a unit, that would be minus 1 and 1 vector right there. That's the L prime vector. Now we very carefully, I hope, on your graph made the half sum of these two. That's the phase vector, the P vector, and the half difference. That's this line right here, but that we bring down so that it is based at the origin of this graph. So we should have all of this stuff in positions here. And then it's just a matter of adding these two vectors appropriately. The basic idea of having this thing be a half sum, and the other one, a half difference, is just the construction that we need to make here. So I'm going to go ahead and bring this forward here, showing those vectors in the places where they exist. So this one, actually, if we're going to use the frequency that Alice and Carla originally had before we did this tuning trick, they both had 600 terahertz, so that was 2, and so the actual vector here is 2 times minus a half plus a half, and I'm putting the frequency that they would have in their reference frame in if we think of Bob as experiencing the light from two moving sources going out 3/5 the speed of light. Now, see if there's anything else I need to mention at this point. Basically, it's really very simple in that the good old pitcher's mound here and the group vector, this one here has this value for the frequency and this value for the wave number times c. Remember, that's a frequency too. In order to do geometry, we try to multiply by whatever factor that gives us the same scale on both sides, both axes. So this half sum of the Doppler shifts written in exponential form gives us a hyperbolic cosine for the call it x coordinate, but it's the ck coordinate actually. This distance right here, and then the difference in these is the hyperbolic sine, so the altitude here. If I'm not mistaken, I may have said that backwards. Not I have. The frequency is the first thing we write down. That's the vertical axis. And that distance right there is the hyperbolic cosine. So let's get that onto the graph. And you just need a ruler to do that. First, the half sum that gives us the hyperbolic cosine. I'm going to put a ruler where that would go. And I'll just draw it sort of as a dashed line just to indicate that it's an important one. This will actually be, when we go to the next step in this, which is to talk about the quantum mechanics, this will be the Hamiltonian value for this particular speed. And this will be the value of the relativistic and quantum momentum. And that's the horizontal thing that is the hyperbolic sign here. So I'm drawing a horizontal line with that, and I'm going to label it in a way that makes it fairly clear where everything is. I will just write it outside here, hyperbolic sine, cosine cosh rho, and this multiply, I'm just going to use a base constant, whatever that there is and whatever units you want to use. I'm going to call that the base or bottom of the energy scale that we're going to be drawing here eventually. And then this one will be a V hyperbolic sine of rapidity rho, whatever that number comes out to be. That number isn't a nice integer, but everything else that we're doing here are rational fractions. That makes it really convenient to talk about what we're going to be making here. So we end up here with one of them being the p vector here being cosh cinch, and then this one down here using the group frequencies as opposed to the phase frequencies, basically changing the sign in both of those. This one gives us a hyperbolic sine going up and a hyperbolic cosine going across. So I'm going to go ahead and do some dashed lines for them as well. So this vector right here, assuming you've drawn it correctly, this is the time to label its coordinates with the same sine and hyperbolic sine and cosine that the pitcher's mound has, the phase part. This is the group vector right here. And we'd be seeing right here a hyperbolic cosine. So that's the length of this, times a constant that's going to be in front of all of our trig functions. We call it the bottom constant or base constant. And I'll explain what that is later on. Now, I will warn you that that is going to be in the relativistic quantum diagram, which is going to become, that will be mc squared, where m is the mass of this box of light. So this box of light is going to have mechanical properties that are relativistic. That's what we're going to be deriving before we're through with this. Okay, so see if there's anything else that I need to point out there. Now, I have, in addition to this, I'm going to go ahead here and escape from the literature, and I'm going to go over and I'm going to pick up the actual drawing that we're making here, and I haven't written everything on this. This is, turns out, for the kind of geometry we need to do, the keynote is actually pretty clumsy, but that's what I have here is a picture of the components that we've just written, and I haven't put the labels on there, but they're on the blackboard. Now, some circles are needed. The hyperbolic cosine and hyperbolic sine and the original base value need to have a circle. All of this geometry here reduces to eventually circles, but one of the things we have to do is build a hyperbola fairly quickly here. In any case, take your compass and go to the 600 terahertz, which is the base frequencies that we're talking about here, and draw a circle from, well, it should hit the 2 over there, and -2, and then +2 on the other side. So it's a circle of radius 2 in these units right here, 300 terahertz units for frequency. And while we're at it, it won't hurt for me to go ahead and label this axis as frequency, inverse time, and we're talking about nu, and that's going to be omega, when we get around to actually making sines and cosines of things, omega over 2 pi. And then down here, we're talking about the kappa axis, this axis that's labeled on your graph paper already, but I'm going to get it on mine. We're talking about C kappa. That's CK prime over 2 pi. And just to always indicate Bob's coordinate system with primes, he's the odd guy in this mix, so maybe that makes sense. So a prime on every one of these quantities will make it look like the graph that we'll see in finished form later on, and check that out. Okay, see if there's anything else I need to do. So I'd get those units up here. This is C kappa, C wave number, C in units of Kaisers. If we were doing CGS units, the Kaiser is literally an inverse centimeter. C kappa is C times what we're used to in physics, K, divided by 2 pi. And we've got actually primes on all of those things, so I won't bother to put them on that one up there. Okay, so now we need a circle that, and this is the really kind of interesting part of this. This is where the geometry of Thales comes in to help us. Basically, we're going to draw a circle that has exactly the hyperbolic cosine radius in units of the base, and that would be 600 terahertz, 2 units. What I need is the very precise, as precise as you can do, a circle that goes through the pitcher's mound, centered directly below the pitcher's mound. And in our units, that's, let's see if I've got that right, that's 1.5, which is halfway between 1 and 2, is where this circle has a center. And so you need to draw that. Now, to check that everything else is right, this should go through the base frequency. This circle right here, if I've drawn it correctly, and I've hit it pretty close, right there, it should go through there, stay outside of that line for a while, then go back inside the line and go right down and land on the red shifted frequency. And then on the other side, if this is going to work, if this is right, this should go down and hit on the blue shifted frequency on the other side. And I'll just go ahead here and hope for it to do that. Okay, and that means I've got to be careful because mine easily slips. But this is the main circle we're describing the geometry that we have that involves a hyperbolic cosine, and hyperbolic cosine is the time dilation factor also for the space-time. We're working in per space-time here, so keep that in mind. But what's really neat is, except for a flip of the P and G, except for interchanging those, the graph that we get in per space-time should be a copy line for circle, line for line, circle for circle, of what you have in the space-time. Space-time and per space-time should be, this is symmetric lattice that has that, oh, and let me make use of something I put in here. I'm going now to click on this particular number right here and go directly to where we are. This is midway through this lecture 29. Okay, so we've already looked at a movie several times there that has this particular case. Then on the far screen we have the slowest movie I could make with this particular application that TC has put together. That one over there has us having a battle between 5 and -4. So the light that we're going to make for that is going to be going at 1/9 the speed of light. And you can see the slope of the G vector on the far screen there is, I should go and grab the mouse here, if it points to that, if you're looking at 5, which we are, as the high frequency, and then the low frequency is the number 4, but of course it's pointing the other way. Just this formula is very simple. It's a half sum over a half difference, or a sum over a difference. And I'm going to be doing a 5 plus 4 over 5 minus 4, or vice versa, 5 minus 4, which is 1, over 5 plus 4, which is 9. So this is something that's just cruising along at what we consider a sedate speed of 1/9 the speed of light. Meanwhile, the phase here is really ripping, and you can see it ripping across the screen in space-time. TC put in a thing that draws a little line whenever the 0 of the phase occurs. And of course, as it goes, it makes a gently sloping line that has exactly the slope here of the G that we're drawing in per space-time. So that's an extreme case for what we're doing. Here things look like they're more sedate. We have here something that is also faster than light. I'm going to make that point many times. The phase is the quantity that never goes slower than light. It's stuck in the high end. Infinity minus infinity, that's where it's resting. Now you probably said, let's see, he's crazy. Doesn't he know that nothing goes faster than light? And that's true. Nothing is going faster than light here. Nothing are zeros. This makes a nice joke, right? Okay. Meanwhile, the other vector here, which is pointing up, the slope of this vector right here, is 9. So it's telling you that speed, the speed of that, is 9 times the speed of light. Much faster than what you're seeing the zeros going here. Much faster. They're only going 5/3 there, which is the inverse of the speed that we're talking about here, which is 3/5. Okay? So it's a 3-4-5 triangle. We're just going to be working with that. That's going to give us all of the dynamics, physics, kinematics, and quantum properties. Okay, now we've still got another circle to draw here. This one, it worked out for you if you've got. I need one for the hyperbolic sign that's associated with the new pitcher's mound. So I'm going to go ahead and draw that one right here. Now this should refresh our algebra for hyperbolic sines and cosines if it works. And it did work for the first one we did here. So I'm going to try to draw as precisely as I can a circle through the pitcher's mound with my compass on as close as I can to the proper elevation that particular one has, and that's about 2.5. So here we go, with a circle that should, and this is another checking thing that we do here, it should go right through the red shifted frequency. And then come out the other side, and there isn't anything that's immediately ready to greet it up on the other axis, but it should go up and connect to the blue shifted frequency of 1200. And I can see I'm a little bit shy of that. But then I need to continue without shedding too many tears over being off by a width of a line. And I'll come back to the pitcher's mound right here. Okay? Okay, so those three circles, the base circle, the one that connects with the K values, the wave number values, the per space axis, and then this one which connects with the per time axis. These give us a goodly amount of what we need for the geometrical construction of basically these two signs as relativity and quantum mechanics. So, not too difficult, right? Okay, let's go ahead here. We've looked at the animations and all of that stuff. We've looked at the algebra here. And I'm going to go ahead and come back. Let me make sure that there's nothing else I need to say here. I think that's it. In any case, in a minute, we're going to be looking at pictures like this one right here. That's a graph that's been put from one of the figures in chapter 0, and it's labeling just about everything. See if there's anything missing from there. Anyway, these intersections, the real point of this for space-time is, as I said, the geometry in this has to be repeated over here to cover the universe, basically. The X and CT universe. Okay, so we got a big barn over on this side. We're just going to cover it with rhombuses so that it looks like this. And so it's the intersection of these white lines with the time axis. This is the CT axis, and that's the x-axis. Just plain old distance and time. So the Pulaski graph goes in Newtonian, so we've got time going vertically and x going horizontally. But aside from that, too hard to conceive of this. This is built into our brains pretty well. But the distance between the intercepts, and I should really say twice the distance between the intercepts. And the reason I say that is because these vectors here, this lattice, should enclose the full range of the phase, that is 0 to 2 pi. This is 0 to pi, so there's a rhombus right there that just has a wave going up. The darker regions here indicate a trough in the wave as it is registered on space and time. So I need two of these distances right here on each of these axes. Okay, and they're the same distances. So there's a lot of symmetry here that makes this stuff easy to deal with. So you see the same thing happening with the low speed relativity, but that's low speed for the group. It's enormous speed, 9c for the phase. And the same thing is happening there. The actual lattice consists of 4 boxes, a plus a pair of 2 and a minus pair of 2. Okay, now, is everybody following is there any, I mean, this is where you ask questions, because if you can think of a question, ask it. It's important to see qualitatively as well as quantitatively what we're building here. And there are no approximations here to this relativity.
Professor
This
Harter?
is it, as far as we know,
Professor
for a vacuum. Yes.
A quick a reiteration in a statement.
Yes.
You mentioned the reciprocal nature between the P's and the G's when you go from per space, or you're comparing
That's
that to time, space-time.
That's right.
You get a reciprocal nature in the size of the vectors as well.
Good point. Yeah, not just the distances, but the areas. Here we have an enormous area in per space-time. Okay, and that goes with the tiny little double rhombus consisting of a full period that's enclosed by the P vector. The hollow P vector, and that's the thing that is weird. When you go over to draw your space-time graphs, I've taken the convention of drawing little hollow things, but I just discovered this morning that Keynote is not being nice about those particular kinds of fonts. They're called outline fonts. And they actually get some of the graphs out with that. But you, of course, should be aware that the main difference is that the G here can never go faster than light, can stand still like it did for the standing wave. It can almost stand still, if you call going at 1/9 c standing still, near that. But as you go over here and it starts to squeeze in on the speed of light, which is 45 degrees on this graph, then that's getting to the limit. And group velocity is limited there. Meanwhile, phase velocity is limited from going infinitely fast to going the speed of light. Now, some of the real magic about quantum mechanics, how they used to liken it to dropping a Coke bottle in at London and having it pop out in New York, in Harvard. I mean, you know, there are waves in the water presumably that would be made by a Coke bottle, and it's almost not too much of an exaggeration to say that the amplitudes are equivalent for that. But yet, what's going on in any quantum process is the phase is just going mad. The phase is just so fast and so horrendously high frequencies. That's the thing that causes the magic in quantum mechanics. And we still haven't sorted it all out yet, but you can see for basic things that is really what we're dealing with here. Classical mechanics gone mad. Okay. Anything else? Yes.
I've got
thank you.
a few questions. This might be like really basic, like going back to the beginning.
We need to.
Yeah, I take two lasers.
Yes.
They have the same frequency.
Two
let's say they
lasers
start with the same frequency.
Two lasers with the same frequency. And this is easy to go ahead and set up here. Let's do it on this one since it's the thing. I'll just go, let's do 4 and 4. That's what makes the Cartesian grid.
Okay.
Okay?
So they're shining in opposite directions.
All of these are having
They
a
have to meet.
collision. This is a collision
Right.
between
Okay.
light.
Or in a box. When you get
Yeah.
Right. And so if I just start moving towards one or the other, or I just adjust the frequencies, do I start with per space-time or
Yeah, be
space-time?
careful.
What's like the...
Be careful, there was a little bit of a slip of the tongue,
Yeah.
I guess, there, because when you start moving, you're not going to change the speed of any of the light,
Right.
okay? Any of the 1 CW light, okay?
Right.
Okay, that's not going to happen. We made that C really
Mm-hmm.
important, right? And rigid and, you know, can't change it. But frequency,
Will change.
yeah, you're going to run into more packets,
Mm-hmm.
crests going into it than you are running away from it.
So I guess one thing maybe I missed is, how do you say you've got like the two frequencies? How do you
Which
find
we do.
from that what the speed of the how fast you're moving?
Okay, we're going to answer that in just a little bit.
Okay.
So that is a really good question. That's the number one question. How fast does this arrangement go? Right.
Right. So I'm wondering,
And
how
we're
do you
kind
know
of seeing
3/5
that by the
gets you?
slopes, but we need to quantify that
Right.
algebraically. And remember that to do that, you simply have to take whatever the K is of whatever it is. It could be a group K or a phase K. And you got to take, if it's the group you're interested in, you got to take the group frequency. So you got to take the per time, put that in the numerator, okay? And in the denominator, put the per space, which is the K or kappa. So the formula that most people in physics remember is omega, that's per time, but with 2 pi. And then K, which is per space, but with 2 pi, okay? The 2 pi's cancel, and so that's equal to nu over kappa, and we're working with nus and kappas here, okay? It's frequency over kappa, so it's per time over per space. So it's per time per space, which is just space per time. And that's something you should have in core. That's something you should have, you know, glued to some neuron in your head. And it took me a while, so it's going to take you maybe, some of you a microsecond, some of you a year. I mean, these are things I'm going to be talking about that are very fundamental, as you say, are things that you want, if you're going to work in modern physics, to be right there on the tip of your tongue or wherever it is that is accessible. So that is what we're getting to very shortly here.
So I could just pick, since we don't really know how fast it's going yet, I could just pick 2 lasers with 2 different frequencies and just go from there?
Yes.
Okay. And figure out how fast I have to be going for that?
Yeah, you got to know the frequencies,
Right.
and it's going to be half sums and half differences playing with each other. And that is basically what this graph is all about.
Okay.
Is that okay? Well, thank you as usual for the question. Eric.
The area of the cells here is invariant.
The area of.
So is P dot G equal to P prime dot G prime? Is the area of the parallelogram the same as the area of the original?
Well, you're asking for a comparison, say, between the area of this, let's call it rhombus, just for that, because that's what it is, compared to this rhombus.
Compared to the original
The green, the big unshifted.
rest frame.
Oh! Yeah. That is a beautiful symmetry. Thank you. Well, I was going to bring it up later, but you're too smart. You jumped the gun. But that's good. That's good. Exactly right. And why is that? Because as I run through this thing, and this I would like to really call the time reversal axiom. I say the main axiom we have is that C is really constant, okay? But here, every time I blue shift myself by some factor, and we did an octave here, we did 2, right? I have to red shift by the same factor. That means I have to divide by it. So the area of the baseball diamond that was a nice square is exactly equal to the area of this new baseball diamond right here. And always will be, because this has been multiplied and that one's been divided. So that area is an invariant. And that's going to yield a hyperbola. The hyperbola xy equal a constant if you turn your x and y to be the 45-degree lines. Does that make sense? It'll make more sense as we do that, but that's a really good question. That is the ultimate invariant here that is geometrical. Just the C equal 2.9979245 with no plus or minus is the physics. But then, on top of that, the Doppler shift has got to be product constant. Red and blue, red times blue has to be constant. And that's the area. And the area means something. The area is tied up with action and all that kind of stuff later on. Okay? Is that... Okay, so we've got 2 really good questions from opposite diagonals of the room.
It's this
We
again.
need some,
It's a cheer, but
occasionally some questions from the middle. Okay? All right. Let's get along here. Because one thing I really want you to see, and that's something I'm going to be asking you to do yourself, is go ahead and put in a bunch of lines that are just extensions of these lines. The extensions of the group lines, okay? The group lines, where group lines here are P lines over here, okay? There are things that are going faster than light, and then all these other lines that are more sedate, that is slower than the speed of light. We're going to be wanting the intersection. We're going to know what's the intersection between those pairs of lines. Okay, it's a little bit hard to see, but when we get done, we're going to also want to do it on this axis as well, just to get a complete mapping. See, I'm just showing you here that the period of the phase, okay, is indicated by that distance right there. Now this graph is misleading because I only have one phase in each one of the rhombuses. I should really be looking at the graph that comes after that, this one, where each one of the rhombuses has 4 squares. A downer and a downer on the diagonal, that diagonal, and an upper on that diagonal. Or the reverse. You see, we can look at this one right here, where the uppers, that's the lighty region, is on this diagonal, and the downers, let's see, I should probably be looking maybe at this one. Anyway, it's got to have up and down in it. So this guy right here comes in at 0.8, that's 4/5. We've got to talk about that one. We've got to talk about this one, okay? They all have names that are really important. Let's just go through what they are. The period of the group, the period of the phase, the lambda of the group, the lambda of the phase. So it's really 4 things that are really important here that we got to get off of this graph. That's the space-time graph. It should also show up over here in per space-time, but differently. We've got the frequency of the phase right here, and we've got the kappa of the phase right here. This is kappa, this is a tau. This is space, per space. This is per time. Okay. So these distances that we've just figured out here for sine, hyperbolic, and cos hyperbolic are used by both the group and the phase, just interchanged. They are reciprocals of each other. And this is the table that I collect from all of this geometry here. We're doing all of the geometry of space and time by looking very carefully at the quantities. Velocity is the one you brought up. That's in this column. The velocity of the group here is 0.6, 3/5. The inverse velocity, which is called the velocity of the phase, right here, that's 5/3. That's the biggest quantity on this graph. Or this table, okay, for this particular 3, 4, 5 triangle that we've picked out here, 3/5 the speed of light. That's the classical velocity right there. This is the mysterious velocity that Newton had no concept of. This is the hidden velocity that's making everything have a heartbeat. Okay, the phase, the pitcher's mound, that's where it drives baseball, right? The pitcher's mound. Take the pitcher away, everybody goes home, right? Take the phase away, you got nothing. Okay. Now, all of these quantities that we're playing with here, this is just for the hell of it, but I think there's something to it. They cross each other, and when they do, it's at golden ratios, all kinds of funny numerical stuff going on. We don't have time for that today. It's just a hobby later on. Let's go through this business here. That's the thing that I really want to get across today. It's going to involve the graph that you are making, and we'll put some equations on that graph now. We'll try to get some algebra going to make a table for that. So what I need to do here is simply change me to the actual talk, so that we'll have that on both of these screens. We'll keep those movies going
over there for pretty much all of the talk today. But this one, I want to do big time. Okay, so I want to bring that up to this point. Now, let's stop here a minute, because I did have an answer to your question actually written down here. The slope of Bob's group of vector, okay, is the actual group wave velocity. It means that's the actual classical velocity that we've been working with for this whole course. When we say velocity, that's what we mean, okay? And V group is the sinh over the cosh of rho. Whatever effectors I have, 2 pi, or whatever that is, the shared effector, it's gone. We're just left with a ratio of those 2 hypertrig functions. Now, what we had was 3/2 over 5/2 actually, but that's supposed to give us 3/5. And that is called the relativity parameter. That is the kingpin parameter for the usual description of relativity. This is not the usual description. Rho is our key parameter. Rapidity, the logarithm of the Doppler shift. This is all due to Doppler shifts, but the Doppler shifts have understandable properties, which make the other properties more understandable. So it's a hyperbolic tangent. And that's the one that shows up at the very beginning or end of this table. Everything in this table on one side is the reciprocal of what's on the other side. And then this, whatever's here, is the reciprocal of that. Whatever's here is the reciprocal of that. And these two are going to be reciprocal of each other. We're going to have a sec and a cosh in just a minute here that we work with. But in the meantime, I want to get the phase. I want to do the phase stuff first. I want to look at the phase velocity in space-time, but I also want to look at its per space-time vector, which is the Pitcher's mound vector. Okay, and right now, what we're talking about for this guy right here is 1 1/4. We're talking about 5/4 for that particular vector right here. In the units that we're would be using, we're talking about 1 1/4, 1.25, literally on this scale. Okay. Now this is a scale which makes 600 terahertz the unit, so watch out for that little factor of 2. But that's just for reasons of convenience here. Okay, so the phase frequency. The phase frequency that we're talking about here is this guy here, and that's 5/4. Well, if that's the frequency, then flip that, and you'll get the period of the phase. And the period will be the distance between the intercepts. That's intercepts of lines containing both an up and an up and a down. Okay, in other words, it's going to be 2 of these lines. They come in pairs, just as the rhombus comes in a pair, 4 things. So the phase here is going to be 4/5. That number is the inverse of that number. So that's the hyperbolic secant. Now, getting a little ahead of myself here, but it doesn't hurt to say things twice. What we're talking about here with these lines, okay, and that's what we're getting to in a minute here, is the group. That number right there is a number that is associated with what we call Lorentz contraction. And we'll get to that in a minute, but right now it doesn't really show itself. We need to be looking at the group paths for that. Okay, let's see if there's anything here. I mean, this is basically a game of starting with Dopplers and fill in this table. And the Dopplers are on the end here. Okay. Anything? Yeah. Good.
I think you said this before. Rho is not a nice number. It's
rho, the logarithm of the Doppler shift. The Doppler shift is a nice number, right? 2 1/2.
Right.
Okay. And if you make it a nice number, all of the ones that you do in physics except for the things that have logarithms attached, and it does. I take a logarithm of 2, and I take a logarithm of 1/2. I don't have a nice number, right?
Okay.
Okay, so that's a
is
good question.
a way to like see it on this graph? Is rho anywhere on the graph, or is it just kind of
Rho
hidden?
came before. When we
Okay.
talked about Alice and Bob and Carla comparing their relative speeds by comparing their relative frequencies,
Mhm.
right? And we showed that rapidity is really a nice number in the sense that it adds and makes Galileo so happy he actually smiled for the first time in his life.
It was also represented as an area sector beneath the hyperbola. So when you cranked up the velocity, your rapidity went up as well, the area.
We'll see more of that, I think, shortly here. Yeah. So that's an excellent question. But that main parameter, and neither will beta necessarily be the old parameter. Okay, it's on the table too. There's the table up there, but we're going to have I don't see. Yeah, here's beta down here, 3/5. Okay.
It's not far down here.
All right. Anything else? Okay. Well, let's take it to the next level here. I'll go ahead and do it on this one. Just to think that's the one you should look at it to make connection with the rhombus. It has 4 sub-rhombuses. That's important to have. Okay. Here's the other side that we just talked about of the phase. So we've taken care of the 2 quantities that are associated with the phase. We have the velocity yet to go. And this is really important in the sense that I've already said it once, I can say it again, and that is the magic of the phase is that it's always faster than light. In this model, okay? It's a model that very clearly shows its role, and that is to go really fast. So here we're talking about something that the frequency factor is 1 1/4. That's 5/4. We're talking about a kappa that's 0.75. But the ratio of those two, 5/4 over 3/4, is 5/3. Okay. The inverse of that phase velocity is of the group velocity, which is 3/5. Okay, let's keep going here. Now everything that's green is associated with the G, the grandstand, the group. Okay, and I'm looking here at a couple of numbers that are important. The lambda of the group, okay, and that's again, the wavelength. What I call a wavelength is going to be the distance between lines that hold a pair. Okay, I don't just stop right there and measure it, I need double that. And it's a little sneaky because this thing is doubling right there, and then this phase thing is coming through there, so you got to make sure you don't confuse one with the other. Same thing happens up on top here between one of these guys intersecting here and that one intersecting here, symmetric to this. So you got to watch out because those numbers are pretty close. They're not equal, but they're pretty close. And that chart I showed you where they get equal, well, that's interesting. But this one's nice because they're not quite equal. Okay, we're talking about 0.75 and 0.80. So you can have a graph that's accurate enough to distinguish those clearly. So there we go with a group. And while we're at it, we also can fill in the frequency of the group, the kappa of the group, the tau of the group, and the lambda of the group. They're all, see, these numbers get used over again, over and over again. It's so much symmetry here that all of these different quantities get to share a lot. Now, this is a pair of numbers that really is the first thing that you would learn about if you had a regular relativity course. But it might be that you learn it using something besides rho. If you use rho, then we already know that they're made of cosh and sinh, or vice versa. So here's the group with cosh sinh, multiplied by 600 terahertz base frequency, and that's 5/4 over 3/4. And what we do is we simply take the cosh and sinh out of there and put a unit vector in here. That's the original G and P. So what we got here is a transformation from the original G and P into the new GP. Big deal, that's what we've been doing all this time with our GCC. This isn't even really a GCC. It is, in a sense, that it's not orthogonal. It's got coshes instead of cosines and sinches instead of sines, but I'd rather work with these things. They're real and they have nice exponential properties that are kind of cool. But anyway, the picture's now same thing except it's reversed. Okay? So the transformation matrix that transforms the original P and G, infinitely, the G that had zero slope and therefore didn't go anywhere, had zero velocity over space-time, and the P, which has infinite slope and represents something in space-time that goes bang everywhere at once and then it disappears, that is going to be transformed by this matrix to these guys. So there's the Lorentz transformation. And he really worked hard to get this. He was trying to find transformations that would make Maxwell's equations invariant, that would not be affected by it. And he tripped and stumbled for a long time until finally he got what it is we're writing down at this point. These two, those two numbers, 3/4 and 5/4. So, okay, we've got something really important out of the way now. The Lorentz transform matrix. When we need it, it's there, but okay, we've got other things to do here. These are famous name coefficients that lie on this table, and they're worth pointing out, maybe more so physically than the Lorentz transformation. Now, I should mention, Lorentz transformation, the hyperbolic sign is the part that's responsible for turning a now line, that is, originally in Alice and Carla's thing, that's now. But according to Bob, that's what it looks like is now for them. And his now is cutting across their now, going into their past and coming from their future at every instant. So before we get into that, that's a real can of worms in many ways. Let's look at these two numbers here. We've got 4/5 and 5/4. This one is called the Einstein time dilation. Something is dilated here by 25%, 1.25. Okay, we're talking about this number here, the height off of origin of the new group vector in space-time. Group vector here that's going less than the speed of light. It's going 3/5 up this axis, okay? And it has a vertical height that is the hyperbolic cosine. That's the larger of the two. Then this one right here, this thing is kind of weird. This one right here, the 0.8, okay? Where does that guy show up? The 0.8, okay? It's the sec, it's the inverse of the cosh. These two things, one of them named after Einstein, who's according to history, the first originator of all this stuff. And then Lorentz, before Einstein, had this other factor already cooked up, the 1 minus beta squared. This other one's the inverse of that. Okay, so these are famous name factors, and this one is the one I want to pick on just for now. This one kind of comes along with the territory, but this one, this Heinrich Lorentz, this is 1853 to 1928. He was right in the relativity is right in the middle of his life here, so he's been working on it before 1905, and he's got all the formulas, but he doesn't realize it, can't figure out what the hell it means. And Einstein has a pretty good, much better idea of what it means. Okay, so let's go ahead on this one while we're at that. I want to talk about that Lorentz effect, the effect of foreshortening distances. That is, if I have something here that's got a certain group velocity to it, it's going to be that much shorter. It's going to be basically 1/5, it's going to be 20% reduction is going to occur. And that's something hard to get your physical mind around. How in the world does something, like a piece of Invar that you have in your lab that you've picked out because the thermal properties of it don't allow it to change much with temperature, so that you can do really fancy optics, right? That thing is going to Lorentz contract. How does that happen? How can something that... What we're doing here is we're using the most ethereal thing in the universe, which is light, and very carefully counting up its parameters in table here. And the group velocity and the wavelength of the group waves. Okay, that's the thing we're really looking at. And okay, waves shrink, waves expand, right? Yeah, I get it. But what in the heck does that have to do with things that don't readily expand and contract? What does it have to do with that? So I had to think of some stories to tell about that. Okay, it's something that I kind of put in a text, but it's something you just read over on. I'll come back later. So what I want to show you is, first of all, what is weird about this contraction is that, for example, what I would see here if I ran my, if I looked at where is 2.0 on the graph up here, okay, in other words, where do I end up? I end up at actually 1.6, okay? 1, if I'd drawn it from 1, this graph right here, and I'm going up here, I would end up at 0.8. So that's probably the one to look at. That's what this number is. This is 4/5. It's 0.8. So what is this is Bob saying that Alice's equipment, whatever, laser wave and the thing that's holding the wave is shrinking by 20%. Okay. But what's really weird about this graph, and that's the thing that you see on the next slide here, let's put them in both places here. So there's both of them. If you go and see what this one is doing, well, there's 1.6. If I come down from here, I'd be on 0.8. Okay, just follow the thing along this line right here. It runs right on 0.8. So Bob says Alice is short by 20%, but Alice says, what are you talking about? You're the one that's the shorty by 20%. Okay? So that's the story I want to level with you on. Okay? So it's Bob sitting here, and here come these brave girls who are riding a spaceship of some kind. It goes 3/5 the speed of light. I have to give them credit for that. Certainly, but what's going to happen later is more to their credit, because what he does is he has some way of seeing this galloping wave that we were making here. Okay, and I'm talking about this one on the screen over here. It's really a screwy wave, but it's the thing that's making the crossbars, the spatial axes, the spatial grid lines are being made by the zeros of the real part of this wave. That's what this is all about. That's what we're gauging everything on that particular effect. We're also keeping track of the zeros that are made by the group, the green thing. Those are just what we're already used to, and that's a standing wave that's going 3/5 the speed of light. But these blue things are cutting across there and making something and going 5/3 the speed of light, and doing even faster over there, 9 times the speed of light across this way, you see. Does everyone see that? See what I'm talking about? That blue line cutting across the now line and leaving a white trail, a sort of a contrail. You talk about the chemtrails, right? The crazy people think they're out there, right? Well, these are kind of out there too. It's just that it's a computer graphic. It's really hard to make those. Okay, so what he's saying is this crazy thing that you have, Alice and Carla, is 0.4 microns. not 0.5, which is the half micron that we expect for 600 terahertz. Okay? They've got 600 terahertz, it's just that we're looking at it as it whizzes by, and we and Bob see 20% reduction. And Alice says, no, Bob, you're the one with the short. And she looks at him, just like the graph I showed you, and says, hey, you're 0.4. So what we have here is the most terrible of lovers' quarrel. And the most terrible quarrel is when they're both right, in some sense. Right? So this, you know, you can understand why people resisted relativity for so long. It's just so many things about the speed of light constant, and then this. And then time, that's the other one. But time, once we get this squared away, I think we can do that one real easily. So what do? Okay? What I do is I make up a paradox with a quote in quotes involving just first order Doppler contraction. This is second order Doppler contraction. We've shown it's due to Doppler, right? But it's Doppler shiftings is not quite canceling. And the faster you go, that lack of cancellation gets bigger and bigger until finally it dominates. So what if they had this situation? Bob says, Alice, your laser, and you just have one laser and a frequency that I can quickly measure, the 0.25 microns, that's what it is, okay, is 50% short. Well, why is it 50% short? Because it's blue shifted. Right? What it really boils down to is no one questions the first order Doppler shift, which is behind all of this. Okay? Well, Carla can see this immediately. She says, I'm out of here. These guys have really lost it. This destroys this as a paradox. Now, still, it's bothersome because suppose, and this is what I want to make fairly clear. Suppose, this is the contraction column here. It gives me 4/5 x contraction. Okay, it's either a secant or rho. We'll get to the use of trigonometric functions, which you're welcome to use. As you'll see, they're really beautiful to use. But if I actually have a cavity that holds the standing wave that we've all been looking at, and it's made of invar, you know, invar steel and invar something else. It's just a really hard, it could be made of diamond. It's really as hard as you can imagine. It's not something you squish 20%, do you? So you have to ask, is the cavity also squishing? It has to, because if it isn't squishing, the cavity won't be resonant. The light that's held in the cavity and is resonating is really sensitive to any, that's why you pay so much for invar. Right? Just go, just breathe on the thing, bam, the resonance is gone. You go, oh crap, go turn some knobs and get it back to the right place, right? That's what happens in a laser drop situation, right? Because now it's automatic, you don't worry about it anymore. It used to be really, really hard to get the laser going, okay? So this is what it's really telling you, is that everything in this lab, including really, well, I don't have the picture here, I thought I did, including the occupants of the laser lab are squishing. Everything is squishing. Because everything's made out of some kind of quantum wave which has the properties that we've been describing for a light wave. Everything, even the invar, is going to change exactly. It has to be that way. Suppose it wasn't, okay? I see the thing resonating now. I'm quite a distance away. I start running, it ought to turn off. It doesn't, obviously. That's sort of the punchline for this breakdown of the what is very paradoxical. But when you look at it, all of the paradoxes in quantum mechanics, I think, are just answered by finding out what it is that waves do. They're the ones calling the shots here. Okay, we've got enough time, I think, if we go a little bit over, to go for the next part of this. This is the real geometry of the graph that I'm asking you to make here. And I'm taking the television program Jeopardy as a way to phrase the thing. I'm imagining Bob is seeing light from Carla, and Carla probably somebody over there, and Alice over on this side, giving him the 600 terahertz this time. And she's giving him 300. Okay, so the question is, what velocity must Bob accelerate to? That's bad grammar, but I'll say accelerate, so he sees the beams with equal frequency. In other words, he knows that these waves, from the stuff we've been talking about, makes a group velocity that's not zero. It's really fast. Okay? And we'll talk about that again here. So the question is, to what velocity must he go? And presumably, what he's got to do is get out of the way of this stuff, because if he goes this way, it's going to blue shift and finally give him a suntan. He's got to go this way, because this is just a nice infrared thing, but he's got to speed up so that it Doppler shifts down to meet this one. This one Doppler shifts up to meet this one coming down. That's what the algebra that we're going to do here is going to tell us. Okay? So, the second question, what is that frequency that he will see when he gets to home base for this double beam? Okay? Everyone has a Jeopardy-style answer by question. And the question is, what is the beam group velocity? It's omega group over k group. That's the way we wrote it down. It's just a slope of the in the graph there. And so what I'm going to do is I'm going to have the group difference right here. I'm going to have the k difference down here. And the k is nothing but the omega over c, okay? So the c comes up in the top, and I get to sum of the frequencies that he's looking at here, and the difference of the frequencies. Well, it's 2 pi times those frequencies, but I should rub that in as many times as I can to keep you from making a mistake of 2 pi, which is really enormous, 6.28 when you're trying to get stuff that's right to 18 figures, and you screw up the first one, not good. Okay, but anyway, this is what we're dealing with here. I can take that 2 pi off of both of them and just get 600 minus 300 over 600 plus 300 of the units of c. And so the answer is 1/3 c. That's what he's got to do. Well, that's no small order, right? But the idea is, we're talking about atoms and molecules, they're going to want to look at a place where there is no frequency difference. And what blue shift is equal to a red shift, okay? That's really what you're asking here, is that there is a frequency. It's the blue shift of the left one and the red shift of the right one. And very quickly you get that the B is this, and then you put it back into the equation to get geometric mean. This is something, as I say in this course, that should go on the tip of your tongue or the tip of some neuron that's going to be working. This is really cool. This is really important. So the answer is it will be 424 terahertz, which is a geometrical mean of those two. Okay, that's cool. Now, where do you see geometrical means in geometry? That's the next thing that I want to get here. Let's see if there's another thing that has to be said here, and that is we're working with the difference mean, the arithmetic mean, and the product mean. Those are the three numbers that really swing in this geometrical description of relativity. And so let's get that up here very clearly. And we've already drawn a circle that kind of represents what this is. And it's the setup for getting the curve that we're really going to need for getting the quantum mechanics of matter waves. This is a geometry that makes that. Okay. So once again, we're talking about 3/5 c for a speed, and that's exactly what you get here. But let's just take it slowly. This is your construction of the circle that goes through the phase point. Okay. And what it is doing is it's zeroing in on the geometrical mean of these two frequencies. This great big thing here that's up at 4, and this thing down here that's at 1. Okay? So there's a 2-to-1 ratio between the laser and this frequency. That's the Doppler octave, double. Okay? And there's another 2-to-1 that's between the infrared 300 and the 600 terahertz, okay? But together, they make a ratio of 1 to 4, okay? And it's the square root of that product that gives you 2. And that's the way it's always going to be with numbers that are much more complicated than a 4 and 2. So you will always be finding the geometrical mean here. And this is Thales. This is 600 BC that he's worked this out. He understands this. He understands this in terms of a very important theorem that he's credited with, that rectangles always have a diagonal that can draw a circle that touches the corners of the rectangles at subtend. So if you have a 90-degree angle subtending the diameter, it will make a circle. Okay? But that construction can do more things. But the main thing I want you to see here, first of all, is the arithmetic mean is the hyperbolic cosine. The difference mean is the hyperbolic sine, and it's the slope of those, the ratio of those two, that is the actual velocity that we're talking about. So this is a really cool way just to, snow somebody that thinks relativity is hard. That's nothing but something that they could do in 600 BC. That's cool. But it also provides, and I don't know whether Thales also discovered this, but it also supplies you with a really quick way to make a hyperbola. And that's what I want you to do now. This requires a compass. So if anybody doesn't have a compass, we've got some more up there. We're going to go ahead and make a few points on the hyperbola. I'm talking about the big blue thing that's in this slide right here. Okay? Basically what we're going to do is just pick any old point down here, set our compass to the phase point, the pitcher's mound, and then draw a circle. We don't have to draw the whole circle. You can just go to the line directly above there and put a little tick, tick right there. Okay? I'm going to do the same thing over here. I'm going to start on P right here, and I'm going to make this thing tighter so it doesn't change. I'm going to start right on the 3 there, okay, just to see. Start anywhere you want, okay, and go up, and when you're on the line that's directly above it, make a little tick. You'll be on a hyperbola. Now, what is this hyperbola? In honor of Eric's question, Eric asked about the equality of area, right? What we're talking about is a coordinate system that has a curve in it that's xy equal a constant. X times y, that's Doppler blue shift times Doppler red shift is a constant, right? That's an equilateral hyperbola that we're drawing here. That's not the way it's taught. This is Einstein's great invariant, and it's x squared minus y squared, and x and y, but it's a lot easier to call it xy. That's the time reversal axiom. It's making the invariance of the mass shell. That's what this is called in high energy physics. Okay? So to make hyperbolas, you start out here with the maximum extent of your compass to the P point, the original P point, not the new one, and then just go and make a tick mark above that. Don't make it too long or you'll not be able to do it. And then move over to another line. Set your compass on the P point, come above where you picked to start drawing it, make a dot, okay? And as you do this, let me see, I'm going to do my max, but you guys have compasses that are way bigger than the graph, so you can easily go way out the end of the graph paper to draw a point on the hyperbola and go ahead and see where it comes on the thing. And I've got to make sure I'm on that line, so it'll be right about there. Okay. Now, as you go inside, same thing. Okay, as you go inside the P point, same deal. Okay, locate the original P point, and then come above it. Put a mark. Okay, and so forth. I'll do one right here just for the sake of argument. It's obvious where these are all headed. Every one of these things should be headed on a hyperbola that goes right tangent to that circle. And it should go through this point, obviously. That was the first one we drew, right? But then it should go up, 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 approaching asymptotically, but it takes a long time before it gets to the 45-degree line. So it should be an equilateral hyperbola cruising above the this axis, going through this point, and then going asymptotically to this axis over here. And this is the way you do it with a compass. Okay? So that's a maneuver that I'm going to ask you to do on the final exam, where we come in with blank graph paper at some speed and figure out all of these things. We've got a lot to go yet. We haven't touched the quantum mechanics yet. Now there's more to this lecture, and you should probably take a look at that. There's quite a number of things that come up. Mainly, there's an animation here which shows you how this is actually happening very quickly. You don't have to sweat the compass and the ruler at all there. But here's something I want to point out right away. We've already seen this. The avoided crossing, that's what you're getting. We're doing the top of an avoided crossing. This is what I call the matter curve. This is the antimatter. This is the relativistic Dirac point that's made such a fuss in 2D materials, right? The catch is, it's not really relative because you have to be really close to that point in order to have the hyperbola and then finally a cone. A hyperbola actually is a parallel to the center of this cone, and therefore goes boom, boom. So when we did this in classical mechanics, it was just simply a matter of diagonalizing a matrix and getting the eigenvalues as a function of the perturber, the electric field that took the ammonia molecule and started to make its wave function lopsided. So it was either on one side or the other and not in between so much. And you start with it very much in between the ground state and very much with a node in between on the excited state. This is going to do the same thing. This has a matrix waiting to make this 600 BC, 600, 6th century, 6 plus 2, 8 centuries ago geometry of Mr. Thales. Okay, so that's one thing that I want you to see. Now here's the other thing that we need to talk about, and that is a completely different relativity approach that only goes incy-bincy into the relativity, but it's really spectacular. And that's the one that uses these functions. In other words, you can do all of the stuff that we're going to be doing with energy functions. This is a Lagrangian. It has to be a cosine, but it's actually a sec if you're doing ordinary relativity with a rapidity. If you're using the sigma angle, and that's the thing you should find out how you construct it, is hiding right here. If you draw a line from here to there and on out, that's going to be sigma from the normal axis. And that's the stellar aberration angle. That's what this is. This is the rapidity, or the exponential of the rapidity. This is just the stellar aberration angle straight away. And you'll find out later that this is the exact equation for the relativistic Lagrangian, just as the hyperbola that you've drawn a few points of. And that's, going to be worth points for the artist. And whoever can draw the nicest hyperbola will get extra 5 points on the final exam. So I'll be aware of that. But anyway, this lets us make use of ordinary sines and cosines. And it's a whole different way to look at relativity. But it's so isolated from all of the others. This is a fellow named Epstein, not Einstein, Epstein. And the book's up there if you want to take a look at it. That's a picture of it. He had to self-publish the thing. It's so weird that nobody wanted to touch him with a 10-foot pole. But it also didn't go, and he didn't go and try to make the connection of this with the rapidity, and that's what this graph does, among other things. So there's a lot of lessons just on the psychology and the mechanization, or the procedures that you do to get something accepted in a given field. Okay, and basically what we're looking at is the k vector that's being transformed. The k vector is being transformed by an angle sigma if you go fast by it, because you Doppler shift the longitudinal parts. The transverse parts are very simple behavior. It's following this angle, which is right in that table along with rho. So that, I think, is something that you ought to take a look at, just to see another side to something. And I wish we had more time to do that. But anyway, there's the graph that we've made. There's the solar point, I call it, or stellar point. Okay, that's the intersection of this circle that you drew with this one. Okay, and you draw a line through that. You've got the stellar aberration direction. Now, where does that show up? Then I'm going to zip through this thing. It makes a neat pattern to discuss waveguides. It also makes it possible for us to do that animation in space and time. But this is a typical waveguide. This is one that's close to cutoff. It's got a angle that's really big, a big sigma, okay? I should say this is the one that's far from cutoff. It's way the heck out on the dispersion curve for a mode. But this is the geometry that we've created right there. That's the geometry showing where all of the interesting geometrical constants are for this thing. And here's one that's really close to cutoff. And by that I mean that we'll let it, see if I can run it here. I don't know what it is that's goofing me up at this point. Let me try again.
Close Firefox copy. It tried to reload another version again.
Is that Firefox?
Yeah, this is the third
playing
time in a
games
row.
again. Let's see if it succeeds. I'll do this one again. Close Firefox. Okay.
Oh, you
Let's see if it
close all instances.
Urgh.
So you have an open version of Firefox
Yeah,
running.
because they turned it off, didn't they?
Use your command.
Let's go and do this computer here and see if we can get it to work for us. It's really a beautiful thing to see, because it lets us understand what the waves do in a guide, and they do exactly the kind of stuff that we're talking about here. This is an abbreviation of that graph. The group velocity is just keeping up with the actual motion that it does as it bounces back and forth across the walls. Okay, the group velocity really slow here. It's half the speed of light. But this one is twice the speed of light, factor of 4. Okay, the phase velocity. That's the actual wave that you would record going. That's the actual phase velocity for wave in a TE mode, which is what we're looking at right here. Okay. And this is the geometry, which is the geometry that we're talking about, well, on the graph here. But more to the point, it's the geometry and I'm going to go get back here to where all that is. It's this geometry that makes the table here, but also makes this graph that we've constructed most of. We haven't constructed all of the things that are in the periphery, but the stuff that's in the guts of it is right there, like Occam's sword, because we're using Occam's razor to make the simplest theory of relativity and quantum. We'll stop with that. Okay. We'll see you on Wednesday. We'll do more of this.
The transition to quantum.
Yeah.